Now it's time for us to turn our attention to the details of the E2 elimination pathway. So remember that E2 stands for a bimolecular elimination. Meaning that there are two chemicals or two chemical species involved at the rate determining step. So we've already seen that E2 is favored by sterically hindered substrates in the presence of strong bases. And we've also seen that the mechanism for the E2 reaction is a concerted one. So let's draw the mechanism. So remember that the leaving group is attached to a carbon that we label the alpha carbon. One bond away from an alpha carbon is a beta carbon. Any hydrogens that are attached to beta carbons are called beta hydrogens. So in the E2 reaction, a base, which again is most likely going to be a strong base, accepts a beta proton. The electrons in the bond between the beta carbon and that hydrogen move down to form the pi bond, and that causes the expulsion of the leaving group. And the result is the alkene. Now, the carbons that had the leaving group and the beta hydrogen started out in the starting material as sp3 hybrids, but they rehybridize in the course of the reaction to become sp2 as the pi bond forms. And so for that to be able to occur, for the pi bond to be able to form, orbitals have to be lined up properly in the starting material. There are two conformations that are going to allow that to happen. So these would be called the reactive conformations, which we saw when we looked at epoxides, or the formation of epoxides. So the reactive conformations for E2 are going to allow the correct orbital alignment that permits the pi bond to form. This orbital alignment is the most important thing that you need to consider about E2. It can mean, though, as we'll see with examples as we go forward, that because you have to be in a special reactive conformation, in some cases, Zaitsev's rule cannot be observed. So we'll see what that means as we go forward. For now, let's just look at what those reactive conformations are. So one of them looks like this. And so you'll recognize this. I'm just not specifying what's at the ends of those four other bonds, just the beta hydrogen and the leaving group. And so what you'll recognize is that the beta hydrogen and the leaving group in this Newman projection are anti to one another. And this is called an anti-coplanar arrangement. So that's one of the reactive conformations that a molecule can be in or has to be in for E2 to occur. The other one is going to look like this. So again, not specifying what's at the ends of the other bonds. In this one, the beta hydrogen and the leaving group are eclipsing. And this one is referred to as syncoplanar. So these are the only two conformations through which the E2 reaction can occur. Now, which one of these is more likely? It's going to be the one on the left. It's more likely that the molecule is going to be in that conformation because that's a lower energy conformation. So most E2 reactions are going to go through that conformation rather than the syn coplanar arrangement. The syn coplanar arrangement, though, can become important in cases where a molecule, for whatever reason, can't adopt an anti-relationship between the beta hydrogen and the leaving group. So in certain ring systems that we haven't looked at, that would be the case. So for our purposes, we want to focus on this conformation. So it's more likely for this to be the observed reactive conformation and that's simply because more molecules at any given point in time are going to be in the staggered conformation than will be in a higher energy eclipse conformation. Okay, so the reactive conformation is what we need to look for in order to correctly predict the product of an E2 reaction. So let's take a look at a couple of cases. We're going to start by looking at how you would predict products, E2 products, when you have a cyclohexyl substrate, so a substrate that involves a cyclohexane ring. Okay, the way you're going to do this is the following. So first of all, let's look at this example here and just see what we have going on. So we're going to go through the reaction conditions and see what we're working with. So the first thing we notice is that we have a good leaving group. So the bromine we know is a good leaving group. We have a secondary substrate that has a little bit of steric hindrance at the beta position. And now let's look at the stuff we have around the arrow. So the thing on the top is sodium ethoxide. And you already know that the ethoxide ion, because it's an alkoxide ion, is strongly basic. The thing on the bottom is ethanol, which I'm going to abbreviate ETOH. And ethanol, as we know, is a weak acid, it's a weak base, it's a weak nucleophile, and it's a polar protic solvent. So remember, in a case like this, where you have an alkoxide ion in the solvent of its conjugate acid, it's always the alkoxide ion that you want to focus on. The strong base is going to react way before a weak base or weak nucleophile or weak acid, for that matter, is going to react. So we don't really have to worry too much about the ethanol. It's just being the solvent. It's not going to participate in the reaction. What we want to do is focus on the stronger of those things, the more reactive of those things, and that's the strong base. Okay, so what can we rule out here? Let's see if we can make a list of things to rule out. So which pathways? We can rule out SN1 and E1 automatically because there's a strong base present. So because strong base. Now what about SN2? Can we rule that out? Actually, we can't. We have a secondary substrate. We have a good leaving group. The substrate is only moderately hindered. And so SN2 is possible. But in this question, we're looking at the E2 pathway, so we're just going to focus on that. So how do we predict this? What we're going to do is the following. To predict an E2 product, remember you have to have the molecule in the reactive conformation. That is to say, the beta hydrogen and the leaving group have to be anti to one another. So for an E2 for a cyclohexane substrate, what you're going to do is the following. You're going to draw the chair in the conformation that has the leaving group in an axial position. So you first draw the chair in the conformation that has the leaving group in the axial position, even if it's not the most stable chair. So that's very important. Okay, so we don't care if it's the most stable chair or not. We care about having that leaving group axial, because only when the leaving group is in an axial position can you have a beta hydrogen that is anti to it. So once you have that chair drawn, then look for axial beta hydrogens anti to the leaving group. Okay, so let's do that for this guy here. So I'm going to go ahead and number carbons. So starting at the bromine, and again, you can use whatever labels you want. Remember, you just need points of reference. And now let's draw a chair. And the bromine is going down according to the skeletal formula. And so carbon 1 has to have an axial down bond. There's 3 possibilities. I'm going to choose this one here. So that's going to be my carbon 1. And then I'm going to number in the same direction that I did for the skeletal formula. And I also see that at carbon 2, I have a methyl group that's pointing up. So I'm going to put that in as well. Okay. So the molecule is in the reactive conformation. Now what we have to do is look for beta hydrogens that are anti to the leaving group. The leaving group at carbon 1, that's the alpha carbon, which means that carbons 2 and 6 are the beta carbons. At carbon 2, the group that's anti to the bromine is a methyl group, so we don't have any hydrogen there. So the only hydrogen, or beta hydrogen, is at carbon 6. So that's what the base is going to pull off. So here's ethoxide as the base. So it pulls off the proton, the pi bond forms, the bromine gets kicked out, which leaves us with this as our product. And then we can redraw that in the original format. So I'm going to continue to put the numbers on here. And then we're just going to translate that back to the skeletal formula. Okay, so for this example, notice that Zaitsev's rule was not followed. That's okay. The orbital alignment requirement is more important. So sometimes in E2, Zaitsev's rule will not be followed. Okay, let's look at another example. Okay, so we have another cyclohexyl substrate. And so let's analyze what we've got going on here. We have an excellent leaving group. So the tosylate leaving group is among the best. We have the same base that we're using up above. So we have ethoxide. So nothing has changed about that. It's in a solvent of its conjugate acid, ethanol. So we know to disregard the ethanol and just focus on the stronger reagent, which is the ethoxide ion. So once again, we have something that's a strong base, and so E2 becomes a possibility. The substrate is secondary. And so once again, we can rule out SN1 and SNE1. And that's because we have a strong base. And SN2, just like the previous example, is also possible here because our substrate is secondary and only moderately hindered. So you could probably get some SN2 result as well. You'll get a mixture of things. But for now, we're just going to focus on predicting the E2 pathway. So remember, you want to draw the chair conformation that puts the leaving group in an axial position. So let's go ahead and number carbons. And this time, just to mix it up a little bit, I'm going to number counterclockwise. According to the skeletal formula, the tosylate group is down, so we need to have that in an axial down bond, which again, there's going to be three possibilities. I'm just going to put it in the lower right, which is one of the three. So that's my carbon 1, and then I numbered counterclockwise, so we can put the rest of the numbers on. And now let's fill in the rest of the groups. So the isopropyl group at carbon 4, according to the skeletal formula, is up. And the up bond at 4 in my chair is an axial bond. At 2, the methyl group is directed down. And in this chair, the carbon labeled 2 has an equatorial down bond. Okay. So the carbon with the leaving group is alpha. One bond away are the beta carbons. And so we have these two beta carbons. Okay, now in this case, you have a choice. Of which beta hydrogen to pull off. And so in this case, because there is a choice, the reaction is capable of following Zaitsev's rule, so that's the one that you're going to go for. So let me pause and ask you, which one is that hydrogen? Would you remove the hydrogen at carbon 2, or would you remove the hydrogen at carbon 6? So if you said 2, you'd be right. So the proton is removed, the pi bond forms, the tosylate is expelled, and you end up with this. Okay, now, some of you are probably noticing the weird angle of this methyl group. Notice that the methyl group is now attached to an sp2 carbon, so it doesn't have the same geometry that a group attached to a cyclohexane ring does. Now this is a cyclohexene. So the strange angle of that methyl group compared to what you're used to is simply because this is not axial nor is it equatorial. So it's neither axial nor equatorial because there's a trigonal planar arrangement of the groups around the sp2 carbon. So if we redraw this, using the skeletal formula, it's going to look like this. Let's go ahead and track all the numbers. 1, 2, like so. Okay, so let's write out what it is that we just did. This time, in this example, there are two beta hydrogens. That are anti to the leaving group. So when you have that case, in an E2 reaction, pick the one that gives the most substituted or the more substituted alkene. That is to say, follow Zaitsev's rule. So in this example, unlike the previous one, Zaitsev's rule can be observed or followed while observing the orbital requirement, or the orbital alignment requirement. So that's what you would do to predict products when your substrate has a cyclohexane ring. What if it doesn't? What if it's acyclic? Okay, well, the same rule applies. You're going to need to have the molecule in the conformation that puts the beta hydrogen and the leaving group anti to one another. So let's take a look at some examples. Okay, so let's start by just assessing what we have. We have sodium methoxide. We know that the methoxide ion is a strong base. The methanol, following what we did with ethanol and ethoxide on the previous page, is just the alcohol solvent, so it's not going to participate. We have a good leaving group. And we have a fairly hindered secondary substrate. Okay, so for this example, what's going on? The bromine is at the alpha carbon. One bond away is a beta carbon. Those are actually vanishingly small. Let me see if I can clean that up a little bit. So the bromine is at the alpha carbon, and then one bond away in any direction are the beta carbons. Okay, so the beta carbon that has a hydrogen that we can pull from is the one that I've labeled. Okay, so to make sure that the molecule is in the right conformation, you need to draw a Newman projection. So what we're going to do now is stand over here and look down the alpha-beta bond. Okay, so that's the bond when you're trying to do this for an acyclic substrate, something that's not a ring. That's the bond that you're going to look down in the Newman projection to make sure that you have the beta hydrogen and the leaving group properly aligned in an anti-relationship. It doesn't matter if the beta carbon is on the front and the alpha is on the back, or vice versa. The alpha could be on the front and the beta could be on the back. You're going to come up with the same answer. When that becomes a double bond, potentially there are two alkenes that could form. So one of these two is going to be the actual product. So let me draw those out. So it's either going to be this one on the left or this guy over here. So you're going to get one or the other. You can't get both. Okay, so to predict the product, what we're going to do, again, is draw a Newman projection. Looking down the alpha-beta bond. Okay, so let's do that. All right, so from the point of view that I've shown in the structure up above, what you would see if you were looking down that bond with the beta carbon in the front is that the hydrogen is pointing down in front of you. The ethyl group is to your right, and the methyl group is to your left. On the back carbon, you have a bromine pointing straight up. The hydrogen is to your left, and the tert-butyl group is to your right. Now remember, this hydrogen is the beta hydrogen. And so what it looks like is that the molecule is already as drawn in the right conformation for the E2 reaction to take place. When the reaction happens, remember what's going to happen is that the base pulls off the hydrogen, the pi bond is going to form in between the front carbon of the Newman projection and the back carbon, and then the leaving group gets kicked out. So what is being removed is this piece right here, and there's an alkene in the bond that you're looking down now. That tells you what groups end up on what sides of the alkene. It tells you that the ethyl and the tert-butyl are going to be on one side of the alkene, and the methyl and the hydrogen are together on the other side. Okay, so if we compare that to the structures up above, the one that has the methyl and the hydrogen on the same side of the alkene is this one. So this is the actual product, and the other one is not formed, it's not observed. So to draw this from the Newman projection, you would notice that the ethyl and the methyl are attached to the same carbon. That's this one right here. The tert-butyl and the hydrogen are attached to the same carbon. And that would be the back carbon. Let's do another one of these. Okay, so we have a substrate. It is a secondary substrate with a good leaving group. Just like before, we have the methoxide ion, which is strongly basic. The methanol is just there as the alcohol solvent. The strong base means that we can rule out SN1 and E1. Those are less likely to be the predominant pathways in the presence of a strong base. Now the methoxide ion, which you could also draw like this, CH3O minus, that's fairly small and pretty nucleophilic. So we can't rule out SN2. So methoxide is small, and it's a good nucleophile. So in this case, we can't rule out SN2. However, we can look at what will happen with the E2 pathway. Okay, so what we're going to look at is the following. The bromine, the leaving group, is on the alpha carbon. And we're going to pull a hydrogen from this beta carbon that I've labeled. These labels are pretty murky looking. Let's see if we can get those better. Okay, so again, what you're going to do is look down the alpha-beta bond and draw a Newman projection of what you see. And it doesn't matter if you have the alpha carbon in front or the beta carbon in front. So this time, let's look this way. Okay, so from that perspective, what you're going to see is a methyl group pointing straight up. There's going to be a hydrogen to your left. The bromine is to your right. So that's on the front carbon, which is the alpha carbon. On the back carbon, which is the beta carbon, there's a fluorine pointing straight down. The beta hydrogen is to your right. And then anti to the bromine is the isopropyl group. Okay, so the beta hydrogen and the leaving group are not anti to one another, which means that we have to access the conformation where they are. So we're going to rotate around the bond, rotate around the alpha-beta bond until you get the conformation where the beta hydrogen and the bromine leaving group are anti. So pause the video and draw that, and we'll pick it back up once you have finished your drawing. Okay, so hopefully what you drew is going to look something like this. Now you may have rotated the front groups instead, but you're going to get the same result. So again, it doesn't matter if you rotate the front groups or the back groups, but you're looking to get the beta hydrogen and the leaving group, in this case a bromine, anti to one another. When you do that, you're going to end up with a conformation that looks like this. So once again, it's the beta hydrogen and the bromine that are being removed from the molecule. And so what that shows us is that the methyl and the fluorine are on one side of the alkene. So these are on the same side of the alkene. And the hydrogen and the isopropyl, which we'll abbreviate IPR, are also on the same side. So to draw the product, let's recognize, I'm going to highlight this front carbon, that methyl and hydrogen are attached to the same carbon in the alkene that just formed. So that's this one. What was the alpha-beta bond is now the alkene. And the fluorine and the isopropyl group are both attached to that back carbon. The isopropyl group is on the same side as the hydrogen, as we can see from the Newman projection, and the fluorine is on the same side as the methyl group. So this is the correct product of the reaction. There's one more idea that we can consider when we're doing an E2 reaction or attempting to do an E2 reaction with a strong base. We've been talking about Zaitsev's rule. So Zaitsev's rule, just to remind you, produces the more substituted alkene isomer. But if you were to produce a less substituted alkene, that would be called a Hofmann elimination. So the base that you choose can dictate which of those two you get in cases where you could get either one. Okay, so let's take a look at this substrate right here. So we have a bromine leaving group, that's at the alpha carbon, and we have 2 beta carbons. Now, if we wanted to get the more substituted alkene, that would be the Zaitsev product, which sometimes people will refer to as a thermodynamic product because it's the more stable of the two possible alkenes you could get. If we wanted that one, then what we would do would be to deprotonate. Let's label these as beta 1 on the left and beta 2 on the right. We would deprotonate beta 1 with a strong base that's on the smaller side. Okay, so what's that going to look like? The choices here are going to be hydroxide and methoxide. So those are the smallest strong bases that you know that you could use in this sort of a situation. By contrast, let's say that you wanted to form the less substituted alkene, which is shown down below on the right. That's called the Hofmann product, and sometimes people refer to this as a kinetic product because depending on the base you use, it would form faster than the Zaitsev product. Those are ideas that we're going to push on later on in the second semester, so you don't have to worry about kinetic versus thermodynamic per se right now, because we'll talk about that another time. But to get to that, you would need to deprotonate beta 2. And to preferentially deprotonate beta 2, you need to use a large, sterically hindered base, a base that's not going to be able to get past the methyl groups that are attached to beta 1 to get to the proton at beta 1. A large, strong base that's sterically hindered is going to have an easier time plucking a proton off of beta 2, which is more available and thus easier to get to. So you would deprotonate beta 2 with a large, sterically hindered, strong base. So you probably already have some ideas of who that might be. And if you're thinking tert butoxide, you'd be right. And if you're thinking LDA, you'd also be right. Tert butoxide usually comes with a potassium counterion. Okay, so let's look at an example of this and see what's going on. Okay, let's say that we treat this compound with LDA. All right, so we have a tertiary substrate in this case, which, as you'll recall, can lend itself to an E2 elimination. It has an excellent leaving group. And so what can we rule out here? We can rule out SN2. First of all, because we have a tertiary substrate that's sterically hindered. Second, because the base that we're using, LDA, is a strong base that itself is sterically hindered. So we have a sterically hindered, strong base. So that moves the reaction away from a substitution and more into elimination. What else can we rule out? We can rule out E1 and SN1 because we have a strong base. So that leaves us with E2. Now, if we think about the structure of this compound, OTS is connected to the alpha carbon, and one bond away from an alpha carbon are beta carbons. So we have beta 1, beta 2, and beta 3. Deprotonating beta 1 or beta 2 would give you the more substituted alkene isomer. It's more likely that LDA is going to go for beta 3, because it's less sterically hindered than either beta 1 or beta 2. So LDA will pull a proton off of beta 3. The pi bond will form. OTS gets booted out. And the result is the Hofmann product. So where you have a possibility to form either the more substituted alkene or the less substituted alkene, and assuming that orbital alignment requirements are not impeding either pathway, the choice of the base, a smaller base, is going to give you Zaitsev product, whereas a larger, bulkier base like tert-butoxide or LDA will give you the Hofmann product, the less substituted alkene.